Imagine a perfectly straight hallway whose walls are made of an impenetrable material like a steel pipe. Inside the hallway, a particle can move, but it cannot pass through the walls. In quantum mechanics, the hallway is called an infinite potential well, and its potential energy function V of x is defined as V of x equals 0 for 0 less than x less than L. V of x equals infinity for x less than or equal to 0 or x greater than or equal to L. Because the potential inside the box is 0, the time-independent Schrödinger equation TISE reduces to the free particle form inside the region. Negative h bar squared over 2m times the second derivative of psi of x with respect to x equals e psi of x. Here, psi of x is the spatial part of the wave function. M is the particle's mass. H bar is the reduced Planck constant. E is the total energy, which will turn out to be quantized. The equation can be rearranged to a familiar second-order differential equation. The second derivative of psi of x with respect to x plus k squared psi of x equals 0, and k squared equals 2me over h bar squared. The solutions of this equation are sine and cosine functions, just like the vibrations of a plucked string fixed at both ends. This analogy will help us understand the later boundary condition step. The walls of the infinite well are completely reflecting, which means the probability of finding the particle outside the box must be 0. Mathematically, we require the wave function to vanish at the walls. Psi of 0 equals 0, psi of L equals 0. The general solution of the differential equation from the previous step is psi of x equals a sin of kx plus b cos of kx. Applying psi of 0 equals 0 forces the cosine term to disappear because cos of 0 equals 1. Hence b equals 0, and we are left with psi of x equals a sin of kx. Now impose the second condition, psi of L equals 0, a sin of kL equals 0. A non-trivial solution, a not equals 0, requires sin of kL equals 0. The sine function is 0 whenever its argument is an integer multiple of pi. KL equals n pi, n equals 1, 2, 3, and so on. Thus the allowed wave numbers are k sub n equals n pi divided by L. Substituting k sub n back into the definition of k gives the quantized energy levels. E sub n equals h bar squared times k sub n squared divided by 2m equals h bar squared pi squared n squared divided by 2m L squared. N equals 1, 2, 3, and so on. Only discrete values of energy are allowed, a direct contrast to a classical particle that could have any kinetic energy. The integer n is called the quantum number and labels the different stationary states or modes of the particle, just like the harmonic modes of a vibrating string. A wave function must be normalized, meaning the total probability of finding the particle somewhere inside the box equals 1. The probability density is psi of x squared. For the nth state, we have psi sub n of x equals a sub n sine of n pi x over L. The normalization condition is integral from 0 to L of psi sub n of x squared dx equals 1. Carrying out the integral, a sub n squared times integral from 0 to L of sine squared of n pi x over L dx equals a sub n squared times L divided by 2 equals 1. Hence a sub n squared equals 2 over L, and we can choose a real positive amplitude psi sub n of x equals square root of 2 over L sine of n pi x over L. The probability density becomes psi sub n of x squared equals 2 over L sine squared of n pi x over L. For the ground state n equals 1, the density looks like a single half wave peaking at the center of the box and going to 0 at the walls. Higher n states have more wiggles. Each node point, where the wave function crosses 0, corresponds to a location the particle will never be found. This pattern is similar to standing wave patterns on a guitar string, where the string's displacement is 0 at the ends and at nodes in between. Expectation value of position x. The expectation of x sub n equals the integral from 0 to L of x times the absolute square of psi sub n of x dx equals 2 over L times the integral from 0 to L of x sine squared of n pi x over L dx equals L over 2. So the average position is exactly at the center of the box regardless of n. This reflects the symmetry of the potential. Expectation value of momentum p. Momentum operator in the position representation is p hat equals negative I h bar derivative. With respect to x for a real wave function, the expectation value vanishes. The expectation of p sub n equals the integral from 0 to L of psi n star times negative I h bar derivative of psi n dx equals 0. The reason is that the probability current is 0 for stationary states. There is no net flow of probability to the left or right. Expectation value of energy E. Because each psi sub n is an eigenfunction of the Hamiltonian, the energy expectation is simply the eigenvalue. The expectation of E sub n equals h bar squared pi squared n squared divided by 2ml squared. No further calculation is needed. The particle has a definite energy in a stationary state. These results illustrate a key quantum idea. While the particle's exact position is uncertain described by a probability distribution, certain averaged quantities are fixed and often reflect the symmetry of the system. The ground state is the lowest energy stationary state, corresponding to n equals 1. Its energy is E1 equals h bar squared pi squared divided by 2ml squared. Even at absolute zero temperature, the particle cannot have zero kinetic energy. This unavoidable residual energy is called zero-point energy. Why does it exist? The Heisenberg uncertainty principle states delta x delta p greater than or equal to h bar over 2. If the particle were completely still, p equals 0, its momentum uncertainty would be 0, forcing the position uncertainty to be infinite, impossible inside a finite box. The wave function must have at least one half wave inside the box, which imposes a non-zero curvature and therefore a non-zero kinetic energy. A practical analogy: picture a ball trapped in a narrow valley. Even if you try to place it perfectly still at the bottom, thermal vibrations or quantum fluctuations give it a small jitter. In nanoscale devices, for example electrons in quantum dots, this zero-point energy can be comparable to thermal energies, influencing device behavior. Energy spectrum, classical particle, continuous. Any kinetic energy E equals p squared over 2m is allowed. Energy spectrum, quantum particle, discrete. En equals h bar squared pi squared n squared over 2ml squared. Gaps increase with n. Energy spacing, classical particle, no spacing. Infinitesimal changes possible. Energy spacing, quantum particle, spacing between adjacent levels. Delta En equals En plus 1 minus En equals h bar squared pi squared over 2ml squared times open parenthesis 2n plus 1 close parenthesis. Grows linearly with n. Probability of position, classical particle, uniform. Particle is equally likely to be anywhere because it moves at constant speed and spends equal time in equal intervals. Probability of position, quantum particle, given by psi n of x squared equals 2 over L times sine squared of open parenthesis n pi x over L close parenthesis. Shows nodes 0 probability and antinodes higher probability. Momentum distribution. Classical particle, single value p equals plus or minus square root of 2me depending on direction. Momentum distribution. Quantum particle, not a single value, momentum is uncertain. The distribution is symmetric with zero mean and its width grows with n. Thus, quantum mechanics replaces the deterministic trajectory of a classical particle with a standing wave pattern that encodes probability. The larger the box, big L, the closer the spacing delta E becomes to 0, and the quantum results smoothly approach the classical continuum, an illustration of the correspondence principle. 7. Extension to a finite potential well and discussion of tunneling effects. If the walls of the box are finite, height v0 instead of infinite, the potential is v of x equals 0 for 0 less than x less than lv of x equals v0 greater than 0 for x less than or equal to 0 or x greater than or equal to L. Inside the well, the Schrödinger equation is the same as before, giving sinusoidal solutions. Outside the well, the energy E, which must be less than v0 for bound states, leads to an exponential decay because the kinetic energy term becomes negative. Psi of x is proportional to e to the minus kappa x. Kappa equals the square root of open bracket 2m times open bracket v0 minus e close bracket divided by h bar. Key new phenomena. 1. Wave function leakage. The particle's probability does not drop to zero abruptly at the wall. A small tail extends into the classically forbidden region. This tail is the quantum tunneling probability. 2. Energy shift. Because the wave function can spread a little outside, the allowed energies are lower than those of the infinite well for the same n. 3. Finite number of bound states. If the well is shallow or narrow, only a few or even none discrete levels satisfy the boundary matching conditions. The condition for allowed E comes from matching the sinusoidal solution inside to the exponential decay outside at x equals 0, and x equals L. This yields transcendental equations such as k times tangent of open bracket KL divided by 2 close bracket equals kappa, even states. Negative k times cotangent of open bracket KL divided by 2 close bracket equals kappa, odd states, where k equals the square root of open bracket 2m times e close bracket divided by h bar. Real-world analogy. Think of a hill with a shallow valley on each side. A ball placed in the valley can roll a little over the hill if it has enough energy, but even if it does not, quantum mechanics allows a tiny probability that the ball appears on the other side, like a ghostly leak. In semiconductor physics, this is the principle behind tunnel diodes and the operation of scanning tunneling microscopes, where electrons cross a thin insulating barrier via tunneling. The finite well model is essential for describing quantum dots, quantum wells in lasers, and many nano-electronic devices where confinement is strong but not infinite. Explanation: 8 representative exam-style problems and typical answer outlines. Problem 1 - energy levels in an infinite box. A particle of mass m equals 9.11 times 10 to the minus 31 kilograms, electron, is confined in a one-dimensional box of length L equals 1.0 nanometer. Compute the energies of the first 3 stationary states in electron volts. Answer outline. Write the formula E sub n equals h bar squared pi squared n squared divided by 2m L squared. Insert h bar equals 1.055 times 10 to the minus 34 joule second, m and L, convert L to meters, 1.0 times 10 to the minus 9 meters. Calculate E sub 1, then multiply by n squared for n equals 2 and 3. Convert joules to electron volts using 1 electron volt equals 1.602 times 10 to the minus 19 joules. Present results: E sub 1 approximately 0.376 electron volts, E sub 2 approximately 1.50 electron volts, E sub 3 approximately 3.38 electron volts. Problem 2 - normalization. Show that the wave function psi of x equals a sine of 3 pi x over L for a box of length L is normalized when it equals square root of 2 over L. Answer outline. Write normalization integral from 0 to L of absolute psi squared dx equals 1. Substitute psi and evaluate integral from 0 to L of sine squared of 3 pi x over L dx equals L over 2. Solve absolute a squared times L over 2 equals 1, gives absolute a equals square root of 2 over L. Conclude A equals square root of 2 over L positive real choice. Problem 3 - expectation value of position. For the ground state n equals 1 of an infinite well, compute angle bracket x angle bracket. Answer outline. Use psi sub 1 of x equals square root of 2 over L times sine of pi x over L. Set up integral angle bracket x angle bracket equals 2 over L times integral from 0 to L of x sine squared of pi x over L dx. Use identity sign squared theta equals open parenthesis 1 minus cosine 2 theta close parenthesis divided by 2 and integrate. Result angle bracket x angle bracket equals L over 2. Explain symmetry argument as a shortcut. Problem 4 - finite well-bound state condition. A particle of mass m is in a well of width L equals 0.5 nanometer and depth V0 equals 10 electron volts. Write the transcendental equation for the even bound states and explain how you would find the lowest energy numerically. Answer outline. Inside k equals square root of 2m e over h bar squared. Outside kappa equals square root of 2m open parenthesis v0 minus e close parenthesis over h bar squared. Even state condition, k times tangent of kl over 2 equals kappa. Substitute expressions for k and kappa to obtain an equation in E. Use a root-finding method, for example Newton-Raphson or bisection, on the interval 0 less than E less than V0. The smallest root gives the ground state energy. The corresponding wave function decays outside the well. These examples illustrate the typical steps students must master: writing down the correct formula, performing integrals, applying boundary conditions, and interpreting the physical meaning of the results.